Let B be the set of rectangular boxes with surface area 54 and volume 23. R, the radius of the smallest sphere that can contain each of such boxes. Find the value of R squared. Consider any such a box in the set B with dimensions A by B by C. Then its volume is ABC and the surface area is 2 times AB plus BC plus CA. A sphere can contain a rectangular box when its diameter 2r is greater than or equal to the diagonal of the boxes, which is calculated as the square root of a squared plus b squared plus c squared. Given a fixed volume, the diagonal of the box is long when it has a long length and a relatively shorter width and height. However, there's another restriction on surface area, and the length of the box cannot be arbitrarily long. There must be a range for it. This is the intuition behind the problem. Let's rephrase the problem. Let A, B, and C be positive numbers such that A times B times C equals 23 and AB plus BC plus CA equals 27. Find the maximum value of 1/4 times A squared plus B squared plus C squared. We have three variables A, B, and C with two equations, so there is a 1 degree of freedom. Theoretically, we can solve for B and C in terms of A. First, B times C equals 23 divided by the A. This is from the first equation. From the second one, we have AB plus AC plus BC, which is replaced by 23 divided by the A, equals 27. Solve for B plus C, which equals 27A minus 23 divided by A squared. Now, we have B times C in terms of A and B plus C in terms of A. By Vieta's formula, B and C must be the roots of a quadratic equation, x squared minus 27a minus 23 over a squared times x plus 23 divided by a equals 0. This quadratic equation has real solutions B and C, so its discriminant must be non-negative. The discriminant is defined to be the square of the coefficient of x, that is 27a minus 23 squared divided by a to the power 4, minus 4 times the leading coefficient, which is 1, times the constant, 23 divided by a. This inequality will determine the range of a. Also, B and C satisfy the same inequality because they are symmetric. For example, we can express A times B and A plus B in terms of C to come up with exactly the same inequality in C. Let's solve the inequality. Multiplied by A to the power 4, the left-hand side becomes a cubic polynomial in A. Then, multiplied by -1, the leading coefficient for a to the power 3 is a positive integer now. And the inequality sign is switched. It's less than or equal to 0 now. The next job is to factor the polynomial. Because the coefficients are integers, we first consider rational roots of the polynomial. The rational zero theorem states that a polynomial with integer coefficients will potentially have rational roots in the form that a factor of the constant term divided by a factor of the leading coefficient. In our case, the constant is 23 squared and the leading coefficient is 4 times 23. Well, there are a lot of choices. We can narrow down the search. We have 23 as a factor in the first term and also in a constant. So, in 27a, it should also consider a factor of 23. In other words, if a is a rational number, its numerator must contain 23 as a factor. As a matter of fact, 23 over 4 is a root of the polynomial. We can see this in a different way. We can split the term 27a into two terms, 23a plus 4a. This way, all the coefficients contain only two numbers, 4, 23. 23 here, 4, and 23. Then we expand the square. The leading term, 4 times 23a cubed, and then negative 23a squared, negative 2 times 23a times 4a minus 23, and then negative 4a minus 23 squared. Then combine the first two terms and factor out 28 squared. It remains 4a minus 23. And in the last two groups, 4a minus 23 is also a factor. Factor that out, we have 4a minus 23 times a quadratic polynomial in A. We end up with three real roots, one rational and two irrational. They are arranged from the smallest to the largest. For the multiplication to be less than or equal to 0, either all three factors are less than or equal to 0. This is the first case. A is less than or equal to the smallest root. Or one negative factors and two are positive. This is the case that A is between the second and the largest root. In both cases, A cannot exceed 23 divided by 4. Otherwise, all factors are positive. Let's see what we have with this longest length 23 over 4. Plug in the equation and solve for B and C. We have two equations for B and C, and we have double root, both B and C equal 2. Then we can calculate the square of the radius. Is this the final answer? This is the last problem of that exam. If you are running out of the time, you might just go with the answer and call it for the day. And your intuition is indeed rewarding. It is correct. But why? Can we prove it? Let's rephrase the problem again. A, B, and C are positive numbers such that A times B times C equal 23 and AB plus BC plus CA equal 27. Prove that A squared plus B squared plus C squared is less than or equal to 657 divided by 16. By symmetry, all A, B, and C are less than or equal to 23 over 4. Therefore, A minus 23 divided by 4 times B minus 23 over 4 times C minus 23 over 4 is less than or equal to 0. All three factors cannot be positive. The equality holds when one of the A, B, or C equals 23 over 4. This is consistent with the original setup. By the end of the video, I will further discuss the idea behind the inequality. Expand A times B times C minus 23 over 4 times AB plus BC plus CA plus 23 over 4 squared times A plus B plus C minus 23 over 4 cubed less than or equal to 0. Plug in ABC and AB plus BC plus CA. We got this inequality. Look, all the terms contain 23 as a factor, which can be simplified. 4 minus 27 equals negative 23. We have 23 here, 23 here. The inequality can be further simplified. So we see this splitting again. 27 equals 23 plus 4. Anyway, we got an estimate for A plus B plus C less than or equal to 23 over 4 plus 4. One of the A, B, and C equals 23 over 4, and the other two sum up to 4. Finally, the upper bound for A squared plus B squared plus C squared is established. And the proof is done. We just established the upper bound of the diagonals of all such boxes. Then, what is the shortest diagonals? Using the quadratic discriminant, we estimated the range of the side lengths, either less than or equal to the smallest root or between the second and the largest root. However, if one of the three variables is less than or equal to the smallest root, the other two variables, even they are still real numbers, but become negative. So that case is not acceptable. In other words, the smallest value for all three variables is actually the second root. Then A minus the root times B minus root times C minus root would be greater than or equal to 0. Compare with the previous inequality for upper bound. Here, we just switch the inequality sign. If we follow exactly the same logic, we would be able to establish a lower bound for A squared plus B squared plus C squared. I post the dimensions of the box here. My second comment is about the proving conditional inequalities. One of the useful techniques is to find the equivalent or consistent inequalities. In this video, I constructed such an inequality to derive the desired one. You can see how it is related to the given conditions for A times B times C and AB plus BC plus CA. Moreover, its equality must be consistent with the target as well. If you are interested in the subject, I have another example. Please watch another video of mine, the other side of the AIME-GM inequality. Thank you for watching.